All right. So great to see everyone back here for the second keynote today at AutoMLConf 2022. And it's my great pleasure to introduce to you Anima Anandkumar, who will hold this second keynote today. She's a brand professor at Caltech, where among other positions, she co-leads the interdisciplinary AI initiative called AI for Science. Furthermore, she's also Director of Machine Learning Research at NVIDIA. And as one would expect, she won a plethora of awards and has been featured in numerous documentaries and articles so far. Her research pioneered the development of tensor algorithms, so something that probably most of you are using nowadays. So yeah, really impactful. And it features both rather empirical, but also theoretical research directions, I would say. Today, she will talk about the latest advances in trustworthy AI. So let's welcome Anima. And without further ado, I'll leave the stage to her.
Thank you. Thank you for the introduction, and apologies I couldn't be there in person, but I hope you're enjoying the event. And many of my students were earlier, in Baltimore for ICML. Hope you also got to, be in touch with them, as well as, some of the team members from NVIDIA. So yeah, as you see, trustworthy AI has seen a lot of, it's gotten a lot of exposure in the recent years, but still it is a highly challenging problem to achieve it, right? So we can come up with all the wish list of what we want in trustworthy AI, but to balance all those objectives and to get a system that is both having good accuracy and trustworthiness is a huge challenge. And that's where I think there's a lot of still open questions for both researchers in algorithms, as well as seeing how these methods scale on large-scale models, and think about all the combination of challenges, both from the system side as well as from the algorithm side. So indeed, if we think about designing AI, right, what we've seen come together is the confluence of data, algorithms, and compute. And similarly, if you want to now think about designing trustworthy AI, what's missing in the earlier picture is the presence of humans, right? So we have to think about centering it around humans and the impact on those who would be either using these applications or have their data represented in these applications. So I think that is a rethinking of how we go about designing AI algorithms. And so there are three facets of it I think are very important. The important one is robustness. And this is true even if you don't put human in the picture, right? For instance, many of the AI for science applications that I think about, always domain scientists ask about what is the robustness? If I have various kind of perturbations, will my answers remain fairly similar? And this is indeed also hugely important, for example, in healthcare applications, because there's all kinds of sensor or other noises, and we don't want the outcomes to change significantly based on those aspects. So, and the question is, many of the deep learning models aren't very robust. So can we make sure to ask for the right benchmarks and the right algorithmic design to enable better robustness? And so this, I would say, is an important facet of trustworthiness. The other is being explainable. And indeed, a question is explainable to whom, right? So at what level do you want the explainability to be? And that means certain abstractions, so should it be explainable in terms of regions in the image or frames in a video, or should it be explainable in natural language? We need to develop that depending on the application. So that means you have to involve, the users and the human in the loop to decide what even explainability should be. And we have some ideas on how to go about that. And lastly, the fairness indeed is, or the lack, removing social bias in the outcomes of what AI applications are providing is also hugely important. This is the one that has rightfully so gotten a lot of attention, and especially many public-facing systems providing biased or toxic outcomes is not something that is acceptable, right? So how do we then provide mechanisms to overcome this and enhance fairness in these systems while taking into account that we need to still have good accuracy and good utility from these systems? So what are those trade-offs? So let me first dive into some thoughts around explainability and interpretability. So in order for us to be able to explain the outcomes of AI systems, I think an important one, but one that where a lot of attention isn't paid, is having good uncertainty estimates, right? So we don't expect AI systems to be perfect. I mean, humans are not perfect. Humans make errors all the time, but we, fairly understand on average why humans make errors. When humans cause accidents, right, it's usually something that you can relate to and connect with why those accidents happen. But on the other hand, when a self-driving car gets into accidents, right, it is very not intuitive to humans. And that is, to me, the core of lack of trust in these systems, because if you cannot understand why these systems are failing and when they are failing, and when they're failing, are they being honest about them failing? Meaning, do they at least have the right uncertainty? So when they're likely to fail, do you also have high uncertainty in these systems? That's something that I think is the framework. We need to first ensure that there is good calibration of uncertainty. And this is really lacking in many of the standard AI benchmarks, because we only think about accuracy. We're not talking about calibration of uncertainty. Because once you have that foundation, you can build a lot more on top of it. Because once have calibrated uncertainties, we can ask for more, right? We can actually ask for verification and interpretable tests. So similarly, like how you would test an aircraft or a car with a checklist of what all the tests it should pass, are there some unit tests we can come up with in terms of what an AI system should pass? And can we actually guarantee the regime in which these tests will be passed, right? What are the operating conditions under which these tests are passed? And that's something that is, standard in formal verification and software testing, but still very primitive when it comes to what we do with AI systems, because we don't have systematic tests. We have a test data set, but we only usually measure accuracy there. We may measure a few metrics, and that may change over time. So I think going from there to also thinking about workflows and pipelines for testing, not just for training, but to continuously keep testing, and add a multitude of tests and metrics rather than one metric like accuracy, I think is an important starting point to enable this. And lastly, as I said, we need to think of a human-centric approach, and that means thinking about good user-friendly interfaces. So how do we consume all this information when it comes to understanding the model? Right. And again, it depends whether this is an advanced developer who understands all the details of the model, or is it a user who wants to be assured that they're having a model that is fair or that is robust. So that's also something we need to think in detail. But again, I would say there is much less attention paid to this aspect on how to communicate performance of AI systems to various users and developers. Now, for instance, if you're thinking about large language models, they have a lot of hard issues such as toxicity to tackle. But again, in what dimensions are they toxic, right? When are they producing this? There's lots of works going into detail, but many of them are kind of coming up with qualitative examples of when there is toxic speech or when there is biased generations, but are there systematic way to verify, as well as for the user to say, I want new dimensions where I want to test bias. How do I easily provide that through a simple interface? And these need not be experts in machine learning. So I think that aspect of democratization and transparency is still missing. So this is in a way like my wish list of what will enable good explainability. Because once you have it, on top of it, you can build the actual explanations, right? In terms of whether natural language or whether in terms of regions in the image, whether in terms of frames in a video. But I feel like without this foundation of good uncertainty calibration, good user-friendly interfaces, you cannot still communicate that explainability, and you cannot have trust in those explanations in a concrete manner. And indeed, as I mentioned earlier, there are a lot of historical biases reflected in these data sets. So we should always go back to thinking about data, right? And this has been an important aspect in the fairness and bias community, especially researchers like Timnit Gebru or Olga Rasowski, Meg Mitchell. They have been promoting the idea to first think about the data sets and to document the model cards and the data sheets. And so that's a good starting point. And once we have those in place, there is still the question of how to deal with uncertainty and how to deal with the fact that these models will inevitably make mistakes, but can we calibrate and can we make sure that these models are not overconfident when they're wrong? And that is unfortunately not the case with standard models. I know this is from the gender shade study, where at that time, what were publicly facing gender detection or other facial analysis cloud APIs were not only wrong on Black women, right, but they were wrong with fairly a high confidence. And so this is something even more acceptable than just being wrong. So this is an overconfidence, and this tends to happen more on underrepresented classes. So there's a lot of discussion of lack of fairness when it comes to underrepresented communities in the data set. But what's also another effect is not only are they wrong, but they're overconfident, right? So which I think further magnifies the downstream impact on these communities. And so if you think about why that is happening, a lot of it can be explained in terms of the training mechanism with softmax, which encourages you to be more overconfident, because the higher the confidence, you're getting a better loss function. And hence, you're not only trying to fit to your data set to be accurate, but you're also incentivizing it to be accurate with high confidence. And this is, we had a paper a few years ago where we looked at the angle versus the norm of these logits. And what we see is, if you look at the angle, that is a much more robust measure of the hardness of examples compared to whether when you look at the norm, it keeps growing as the training is progressing. So what we see is the way the loss functions are architected, there is an implicit bias, right? There is a natural tendency to get to these overconfident models. So how do we overcome this, and how do we enhance calibration in these models? And so this is a work where we looked at it from the lens of distributional robustness, because what we want is to have good uncertainty estimation even under distributional shift. And this directly relates to fairness, because what we are asking is, in training data, we have underrepresented communities or classes that are underrepresented, but we also want to have good performance on them in testing time. So there is this distributional shift. There is an imbalance between training and test, but we still want good uncertainty calibration. So you can also think of fairness, being framed in the lens of distributional robustness. So let me start with a simple example here. Let's say we have source data with where the classification task is to classify whether something is a banana or an apple. And let's say we only have red apples and yellow bananas in training data. But now during testing time, you come up with an yellow apple. So this is an extreme case of shift, because this is something not seen in training data at all. In practice, you may have a lot more of like the red apples versus more yellow apples in testing data. So when these kind of scenarios happen, if you're doing your standard empirical risk minimization, if you have sufficiently enough number of examples, you would classify this pretty accurately, but only assuming the apples are red, right? So the attribute of being red becomes a strong signal for classification. So you will use that as a feature. And that's what these deep neural networks do. They pick on what are the salient features that discriminate between the different classes. But now at test time, we are seeing an entirely new kind of apple that is yellow, right? And if we give it to the trained classifier, it will still think it's a banana. So this is an example, an extreme version of what I mentioned in terms of the distributional shift. If we have underrepresentation in training data, then we are not performing well on those samples. And also we may pick up spurious features that may work reasonably okay on training data, but on testing data, there would be a big shift. And not only that it's wrong, but there's also high confidence. So you see the simple example hopefully shows you why there is now more of this calibration error on underrepresented samples. In this extreme case here, the yellow apple was never seen in training data. And so, there is a very high error in calibration, right? So the confidence is also very high while being wrong. And so hopefully, given that this is the issue with standard empirical risk minimization, how do we build in better distributional robustness and with that better uncertainty calibration? So just to kind of give you an intuition on, what this looks like, the way we want to frame this is if you're doing standard risk minimization, we only directly minimize the loss function on the source data, right? But instead, we are saying we want to minimize it on the target data. So we'll assume access to unlabeled samples in the target set or the testing set. And on the other hand, we want it to be robust because we know there is some distributional shift between training and testing data. So we'll have an adversarial risk minimization where we will perturb the source data and we want it to work well even on the perturbed labels. And so think of this as adding more label perturbation, but in a systematic way to increase robustness. And so this you can set it up. But let me show you how the loss function changes. So going back to the example we had, right? So we know that if you look at the density ratio between the samples occurring in source versus the target data, we can see that this is zero because this never occurred in source data. So what's a good signal now, in addition to just using the trained classifier, is to think about this density ratio. So asking if my samples now in target data versus the source data, what is the change in the likelihood? So if this density ratio is nearly 1, you can safely use your trained classifier, right? Because the likelihood of the sample in both source and target data are nearly the same. But on the other hand, if this is nearly 0, we should be lowering our confidence, right? Because if this data sample hasn't occurred much in your source data, you should not be having high confidence. And so what we did is to incorporate this into the logistic function. So what we are saying now is don't just do the softmax in the last layer, but also incorporate this. So there have been efforts like temperature scaling, which also reduce the confidence. But the challenge there is they just do that uniformly. And they also don't work very well with distributional shifts because they can't do it according to the sample. So what you see here is sample-dependent scaling of temperature. And that sample-dependent scaling is based on density ratio. So with the use of density ratio, we can now decide if this sample hasn't occurred significantly in the training data, we should lower the confidence. And in this example here, it's almost now comes to just random chance, right? Because if this is nearly 0, that's what the output would turn into. And so hopefully this toy example demonstrates now what this method is able to do. It is using the density ratio to calibrate the confidence. And so in test data, if there are now samples that haven't occurred very much in training data, and this happens when there is a distributional shift, right? And for instance, those underrepresented classes like Black women that I showed you earlier that aren't very much present in training data, with this we can detect that this is now an underrepresented sample and hence we should lower confidence. Of course, this does not address the core issue that there is unfairness, right? That there isn't good performance on these samples. And for that, we need other methods, other bias mitigation methods, maybe adding more training data in those underrepresented classes. But to me, this is a starting point because if this is all that you're given, your current training data and test data, we want to ensure that we calibrate and get the right confidence measures. And so what we did is this density ratio, we can train it jointly with the task. And to do that, we want to make sure that we train it in a tractable manner. If we could do it through generative models, but that is more difficult to get the correct likelihood. So instead, what we did was a simple task of using binary classifier to classify whether a data point is from the source or target data. So in this example here, we did a big distributional shift between synthetic data and real data, right, as one use case. But you can see you can do it for any data sets and look at the training and target data and see how much you can classify. So the intuition is for those target samples that you can easily classify from source data, that would mean that they're very distinguishable, and so they wouldn't occur a lot in the training data. And so this binary classifier gives you the signal of uncertainty through this density ratio. So you can compute this and train it end-to-end together. So there's a little bit of detail here because in order to train the target task, we don't have labels in the target data set. This is unsupervised domain adaptation. And so, but on the other hand, you can analytically get the gradients through this expression that I won't get into here. So it turns out that you can still train all this end-to-end in a differentiable manner, which makes it very convenient because you're simultaneously calibrating for uncertainty while training for the target task, while also adapting from a source domain to the target domain in an unsupervised manner, meaning there are no target labels available. So that's, I think, the benefit of doing this in a systematic manner while also we see that in practice, if you use this in the loop with self-training, because we want to adapt more and more to the target domain, we can do that using self-training, meaning we have pseudo labels with the current classifier and we want to train on that again, but we only want to do that on confident labels. So if we use this method to get the confidence scores, that is this here, we have a much better performance, but also much better Brier score. So the Brier score is a measure of uncertainty calibration. And so we see that we do well here, and we also reach there much faster than the other methods. And so the other benefit is by using these kind of density ratios, there's good interpretability under distributional shifts. For instance, an image that is more cluttered or harder would have lower confidence than one that is easier, right? So it's also aligning with human intuitions on what is easier and harder. So you can use this as a way to test for which samples are harder, and maybe find other ways or add new data to improve performance on those samples. So this is also valid in many other scenarios, such as drone landing and trajectory tracking, which involves uncertainty quantification. If you want to keep learning to drive at faster and faster speeds, so that means we are extrapolating away from our current training distribution because we don't know what would happen when it goes faster. So using this distributional robustness work means that we can do safe exploration. So we can collect training data at faster and faster speeds while never crashing. So in this first epoch here, it takes forever to land because you're very, careful. On the other hand, in a later epoch, as we progressively train, you can land faster. And we can assess in the next epoch how much faster to go because we have this distributional robustness method. So this way we can progressively land faster while still being safe. So this is a great example of trustworthiness, because now we need to trust the uncertainty estimates, right? Because it's saying what is the safe region versus unsafe region to increase the speed of landing. And if you're wrong, then we crash. So I think this notion of trustworthiness is relevant both in human-centric applications, but also for safety-critical applications such as this. And by the way, this data here in the simulation is taken from a real drone, so it incorporates complex aerodynamics. So hopefully with that, there is a foundation we can use to calibrate our models for better uncertainty, especially even under distributional shifts. How do we maintain good uncertainty calibration? And this notion of distributional robustness and the use of density ratios helps us get a good signal on where we should scale the temperature, on the test samples that are not well represented in training data, we should lower our confidence, which is very intuitive, but it makes all this come together in a nice end-to-end manner. So now let me tell you a bit more about the next aspect on how do we audit AI models, right? So we have trained our AI models. Can we ensure that they pass certain tests? Indeed, there's a question of how to come up with those tests, but hopefully we can do that together with domain experts on what is relevant. And most of the times, it's not just the accuracy metrics, but also many other considerations. And indeed, starting point, as I mentioned earlier, is model cards and data sheets, which are very important to make informed decisions. So in this work, what we said was, can we have verified tests and we let the users give certain semantic specifications and we can audit these models? To give you an example, we can ask for face recognition as an example. How will will this test work will this classifier work, for instance, of whether there's eyeglasses or not, even when the face angle changes. By how much can you allow the face angle to change? How much can you change the lighting? How many occlusions can you add? And if we can provide verified tests saying, there is for certain range of face angles, the accuracy remains more than 95%. So that's then up to the end user or somebody deploying it to decide if that is acceptable to them, right? But it's our duty to give them transparently what is the operating conditions, under what set of face angles does it work above a certain threshold of accuracy. But how do we enable these tests and give certified training? Indeed, there's a variety of works in certified training, but one challenge is it's very hard to get good natural accuracy while also being good in certified training. So instead, what we proposed was to use generative models and build a generative bridge. So in the latent space of the generative model, can we perturb? And can we do certified training based on perturbations in the latent space? Which makes a lot of sense. If you try to perturb in the pixel space, it is very hard to get large perturbations and still get good accuracy. But the idea is in the latent space, we can enable better robustness. And so by building a common generative bridge, so meaning we take a generative model, we take our classifier or whatever the deep learning model is for the current task, and we build a common bridge. So meaning, how do we enable mapping the latent space of this to certain layers of this deep learning model? And with that, we can provide certified training, and we can tell you, how much of perturbations can we have in this latent space. So it turns out by doing this, for instance, on ImageNet, we can have very large perturbations in the pixel domain, right, or in the observed space. Because we are making these perturbations in the latent space, they result in large perturbations in the observed space, as in this example here, you can see there's a big change in the angle. So in the pixel space, it's huge perturbations. And still we can guarantee a good error. So we have good verified, right, like in terms of how much error can we have with verification, and we can have different conditions on the different levels of it. You can have, and what's acceptable to you is something that you can decide. And we can also do this with chest X-rays, which for healthcare, this is important to get such verified tests. This, to me, at a high level, what is needed ultimately is to ask, can we have robustness and large perturbations and still be able to provide guarantees or certificates in terms of how much we can handle? And to do that, I believe that we need to figure out ways to connect this with generative models and think about perturbing in the latent space of generative models, because only then can we come up with controlled generations and perturbations of large amounts and still give good robustness results. So that's the high-level idea in this work. So I think another aspect that I want to address now, I've been talking about social bias, is the very first step is, can we detect this social bias, right? And many times this has become more, I would say, subjective, like people, I kind of ask annotators whether this is socially biased or not. And usually there are some fixed dimensions of bias, such as maybe gender, race, and also certain levels of toxicity, like whether this is right. So there are certain fixed classifications rather than one that can be adaptive and changing to what the requirements of the users are. And so the question we wanted to ask is, large language models have had tremendous success in achieving good generation. So can we use their ability to also detect social bias? Indeed, there are problematic issues in language models themselves, and I'll shortly tell you some ways to address that. But given that they have seen biased text and also non-biased texts, can we use that understanding ability, that compositional ability, to give instructions with few shots and detect social bias? Indeed, few shot instructions have been used for a variety of other applications, but we've been the first to do that with detecting social bias using very large language models. And so the benefit of doing this is it's flexible. As I said, we don't need to train on a limited set of predefined social biases, and we can keep adding new kinds. And this is few shots, so it's label efficient. You don't need a lot of it. And there's no need for fine-tuning in our framework. So we just use pre-trained language models and we don't further fine-tune them, which means even when they're very large, if you have API access, you can use them directly. And so the way we do this is, there's a set of like labeled samples, right? Like, so we have few shots, so we have certain set of labels on which is toxic or not, or which is biased or not. But what we do is we still select only a subset of them to query the language model, because the idea is we only want to use the ones that are relevant to the current test sample or the query, rather than use all of the training data or all of the labeled examples that are available. But we do that by looking at the latent space. So in the embedding space, how close is my query to the training samples available, or the labeled samples of bias that are available? And then what we do is select only the subset that are closer, and we also class balance it. So meaning whether it's toxic or not, for instance, right? So we will take both positive and negative examples. And then we provide this as prompts into the language model, into the pre-trained language model. And we do that with certain templates in terms of, right, showing the analogy of question and answer. Is this considered toxic or not, for instance? And then we can, get an answer for our current query. So the idea here is, indeed, this is a few shot setting where you take your few shots and your query and try to come up with a classification on your query. But here we don't take all of the few shots, but select the ones only that are closest to the query in the embedding space of the language model. And with that, we can come up with a much better relevant prompts here into the language model, and the performance is much better. And what we see is, as we go to larger language models, indeed the performance of detecting social bias, the accuracy improves and is better than these baselines, for instance, here without the language models. And also, you don't need many labels of your toxic or biased speech as you go to larger language models, which is the other benefit. You can do equally well even with larger language models without needing a lot of labels, which is great. And I think another big benefit that these language models provide, as opposed to, say, directly trying to classify whether there is social bias or not, is robustness to noisy labels, right? Because language models already have knowledge about toxic speech or not, or whether there's social bias. So they have some inbuilt knowledge. And if we try to do a highly noisy flipped experiment, right, then it's still fairly robust compared to, indeed there is performance drop, but there is more robustness than the earlier, than say here, this is a small language model, but also compared to other baselines. And so by robustness, what we mean is here, if you're flipping this from the correct one, in a way, the performance degrades a lot, and it is saying that this can't be correct, right? This is not common knowledge. So what you're giving me is wrong labels about whether this is toxic or not. And so that's an important thing. Like if you're doing a severe flip, the performance drastically degrades, which is a good thing because these are completely wrong labels and going against the knowledge of the language model. On the other hand, if there are a few random flips, the performance is fairly robust. And so I think that's the benefit, that it's having this robustness property, which you wouldn't get if you just used all your labeled examples and trained a classifier to classify whether it's toxic or not. So there is the inbuilt knowledge of language models that could be beneficial in achieving these kind of robustness. Yeah, so the benefits of our approach, as I mentioned, is we don't need to fine-tune large language models, which makes it very accessible and cost-efficient. And you can keep creating new definitions of social bias or toxicity. You don't need to go with what's already present. For instance, in a healthcare application, you may have very specific dimensions and requirements on measuring bias than what's existing before. And the other thing is, because we are not fine-tuning, you won't have catastrophic forgetting of the overall knowledge that is present in language models. So this is always a huge issue. And we don't overfit to small data sets of toxicity or bias. And also importantly, we are robust to noisy labels, right? So in the sense, robust here, not, yeah. So we are able to detect when there is a big flip in labels, and at the same time, if it's randomly noisy, we are robust. So we are able to overcome all these challenges and be able to have good properties and keep this lightweight by using a pre-trained language model. Yeah, so I think these language models and their knowledge can be used for beneficial cases, such as detecting whether a speech is biased or toxic based on their ability to generalize and based on their ability to take few short instructions effectively. So I wanted to show you a bit of overview in terms of what are some approaches towards mitigating undesirable bias. And, we talked about language models being useful for detecting this. But what if we want to fix the toxicity and bias that is present in language models? So people have approached this as fine-tuning with better data, right? So if you only take non-toxic data and retrain the model, hopefully you will get a better non-toxic model. But the challenge with that is there is a distributional shift. And so there's a challenge of catastrophic forgetting in the previous pre-trained model to now fine-tuning. And there's also the challenge that with this distributional shift, there could be instability in fine-tuning. So instead, what we proposed is to use self-generation because there's less of the distributional shift, and to use Perspective API or certain other tests for filtering out toxic data. So we keep only non-toxic data and fine-tune that again, but do it with self-generation as opposed to curated and existing data sets. And so the benefit is there is still a lot of diversity you can get with self-generation. And with filtering, you can get now better fine-tuned model. And the other thing is, as we said earlier, fine-tuning is heavy, right? We don't want to fine-tune this large language model. Instead, we take certain adapter layers where we only fine-tune these layers as opposed to everything. And so this is very effective now in reducing toxicity while retaining language quality and being able to be much more lightweight in fine-tuning. So this is something that I think will help us even address the inherent toxicity in language models and improve them with self-generation. So a few other approaches I wanted to talk to you about is in terms of, what people have proposed is not just to use the standard accuracy, but certain kind of reweighted accuracy, right? So with that, can we, ideally give groups equal representation even when they're imbalanced in training data. And there's certain metrics like bias amplification. So we want to ask, is the bias amplified from training data after sending it through the model? For instance, in training data, there was bias of cooking and women at 0.6, but after sending it through the model, it amplified, right? It further became worse, which is a well-documented aspect of many of these deep learning models. So can we overcome this bias amplification? And so we judge now algorithms not just by their overall accuracy, but also in terms of how much is the bias getting amplified. And so there are a variety of bias mitigation strategies. So I won't get into them in detail, but I wanted to talk to you about a framework we use to enhance those bias mitigation strategies in the presence of intersectional fairness, meaning there are now combination of, or intersection of multiple attributes, and that's much harder. So there is more bias, there's more marginalization when it comes to intersectional communities. And then at the same time, there is a lot worse performance in these intersections. So how can we make that better? So the idea is we do this with a large number of intersectional groups, nearly 200 protected attributes, right? These combinations of attributes, the number of classes become nearly 200. So the current bias mitigation strategies don't scale well. So we use methods like knowledge distillation and attribute class decomposition to make this scalable. So, the main idea here is you want to have group specific classifiers. So the idea is if different groups have their own classifiers, ideally then they all have good classification accuracy and you don't have bias against underrepresented classes. But doing that when there are a lot of attribute labels, a lot of protected groups or a lot of attribute categories is not scalable. So we do knowledge distillation where we are having the student distill knowledge from different group specific classifiers, and hence you improve accuracy while also keeping the group specificity. And we can also do attribute decomposition in different ways and combine that for group specific classifiers to improve performance. I didn't go into all of the details here, but I think at the high level, what we want to come up with are scaling strategies when we increase the number of protected attribute categories or intersectional groups. And that requires thinking carefully in terms of how do we balance overall accuracy with the ability to also reduce bias amplification and do more group-specific classifiers or group-specific tasks to improve reduce the bias in these systems. So in the last few minutes, I want to give you an overview of a recent work we've done in terms of improving robustness in these systems. As I mentioned, this is something fundamental. And we recently presented at ICML on understanding the robustness in vision transformers. Indeed, there is a lot of it that is still a black box, but we're getting, I think, much closer to understanding what's happening in these systems. And so one aspect we wanted to ask is not just, again, look at natural accuracy, but look at robustness in these systems, right? And so we wanted to ask what happens under different kind of corruptions, whether it's classification or segmentation. And what we see is in standard vision transformers, there is quite a bit of lack of robustness. And you also see that here, here it's ResNet, I guess. So here it's other systems. So there is, in ResNet, for instance, there's also lack of robustness. So our intuition was, can we enhance the visual grouping? So if we can enhance how there is objects get clustered or segmented in the representation, in the attention layers of vision transformer, for instance, then we can improve robustness. And there's also the notion of information bottleneck. In a way, information bottleneck is filtering, and hence we can improve robustness by having better information bottlenecks. And we do see that in current vision transformers, the attention layers do naturally group, right? So there is visual grouping here. You see that in different layers, you are getting whole objects together. So these are naturally occurring through the representation learning in these models. So how do we enhance that? And so what we came up with is not only thinking about mixing in the spatial domain. So we have efficient self-attention mechanisms to do token mixing in the spatial domain, but also now we wanted to do it in the channel domain. So if we are using looking at the correspondence of how different channels relate to one another, we can reinforce this clustering phenomena and enhance the robustness in these systems. But at the same time, this channel attention, we wanted to do it in a lightweight manner, which I won't get into details here. But the idea is we can get the best of both the worlds. And with this, our model is now state of the art when it comes to robustness. So this is, compared to, right, like kind of these are flops and how much are we, this is like a retention rate. So the idea is here you see robust accuracy and clean accuracy, both we have comparison, and you can see here that even a very lightweight model is robust. And so that's the idea. So we can get good robustness and good representation learning, right? They go hand in hand. So if you're able to now here in this example here, get well-clustered attention mechanisms and ones with good information bottlenecks that filter out perturbations, that leads to better robustness. And so I think the natural accuracy and robust accuracy need not be a trade-off. We can get both together through good design and good principles. And I think that's the takeaway with these results here, both for a variety of tasks here that you can see in the paper. Yeah, so to conclude, I think, I mentioned this trustworthy AI has several facets, explainability, right? And they're thinking about first having the ability to have good uncertainty calibration, especially against distributional shifts, is very important. Fairness, and that starts with even detecting social bias or toxicity. Can we use large language models to do that effectively? And then can we correct for those? And what are the bias mitigation strategies? And how do we scale them up to many intersectional groups? And at the same time, keeping natural accuracy to be at a good rate. And I think that is an important consideration for new algorithm design. And robustness, by showing you with vision transformers and well-principled design, we can get both robustness and good natural accuracy. And that comes from better representation learning and filtering through information bottlenecks. So hopefully we can achieve all this together. Yeah, so I know I had a broad coverage, but I hope you extracted some general principles from these various works. Thank you.
All right. Yeah. Also, thank you very much from my side for this very interesting talk, Anima. That covered really a lot of interesting topics. So thanks a lot. Are there any questions from the audience already, or maybe even in the chat online? All right, so maybe while you think, then let me ask the first question. regarding the second part on verification, so if I got that correctly, this is mainly empirical verification, but not really in terms of proofs. So I was wondering, do you have problems there with error propagation if this generative network actually is, I don't know, not so well trained and maybe doesn't really generate good images?
Yeah, that's a great point. So it is a certified robustness in the sense we can certify, what is the range of perturbations in the latent space of the generative model for which, right, there is a certain level of error. But indeed, you're right. If the generative model is not having good coverage or good generation, right, this does not work well because we are all hedging in terms of having controllable generation and being able to perturb the latent space there and give robustness guarantees. I mean, the benefit is we don't need to think about perturbations in the observed space. So this becomes a lot more efficient in the range of perturbations we can achieve. But indeed, this relies on good generative models. But we are seeing a lot of that also improve, right? We are getting really good generation these days, and indeed, even compositional in terms of entirely new properties that aren't seen during training.
Okay, thanks. Then there's a question over there from Marius.
So also from my side, thank you very much for this very awesome talk. Since we are at the AutoML conference here, so I have to ask that, of course. Do you see any way that explainability of automated machine learning is actually important? So not only about the model itself, but also the process to get to the model actually.
Right. You're absolutely right. And, like I mentioned, model cards and data sheets, right? That's a good starting point, but that doesn't cover everything in terms of, right, how the model went through iterations, and especially if it is getting automated, what algorithms were used to, right, automate and get to the current model, and what metrics were used. So I think, what we need is the transparency of those algorithms, but also maybe like a way for users to interact with those algorithms, right, in a dynamic manner. So they get to choose and maybe ideally tune parameters so they get personalized models based on their requirements rather than one fixed automated method choosing what the metrics are to come up with an algorithm.
Hello, thanks for presentation. I have a question about the first part, which you say about the label data. I believe that you have 35,000 baseline for the label data. Is kind of require at least 35,000, and from one domain to another domain, is it still need another label data?
Sorry, I don't know where the 35,000 was. Maybe
the slide in page, I think that was a colorful green, red. There was a D data set.
Sorry, are you talking about the distributional robustness?
Few prompt instruction.
Oh, few prompt instruction. No, indeed we don't. I mean, that's the idea that was the base set, but we only selected like a few, I forget, maybe 20 to 30 to go with the query, right? And we can do with much less. And those were the ablated studies where we did 1,000 or 500 or even less. So because that's the social lens data set, but we didn't use all of it. And that's the message. But that's the data set on which we tested. Yeah, but each time with the query, we only select about 20 to 30 to go into the model as few short prompts. And what we found is even less than 1,000 or even less than 500, I forget the exact number, was giving nearly the same answers, the same performance. So that's the gain here, that we don't need very large data sets, label data sets, to get the good detection of social bias in these language models.
All right, then we have two more questions over here, and then I believe we should end the session in the interest of time.
Yeah, thank you for the interesting presentation. On the first part, where you were using a binary classifier with a discriminative network to kind of detect out of distribution examples, if the synthetic examples are not as good and like the discriminative network is focusing kind of on the small details of the synthetic examples, do you do anything extra on the discriminative network to make them more robust for this use case?
Yeah, that's a good point. So far, we haven't, right? But the idea is if you're not able to discriminate training and test data, but on the other hand, there is something that is shifted, right? Then we need to fix this. So we are assuming this is, right, you can train a good classifier if you can detect these out of distribution samples. But yeah, if that assumption is not true, we would need to further fix that. I agree.
Thank you.
Thanks for the talk. Regarding your paper on adversarial robustness of vision transformer, understanding the robustness in vision transformer paper, I was wondering the key insight that you can share with us was that the power of hierarchical structure or information bottleneck. I would like to understand the key insight and key theory behind it.
A bit more time here, right? So, the first hypothesis, which I think there's a lot of good evidence, is these self-attention layers are really good at attempting to group the object and kind of find what we call visual grouping. So we are able to get the notion of objectness in these layers. So that's happening well, but can we enhance that further? And so the intuition then is that, that grouping is happening because we are doing this spatially, right? So we are doing the self-attention spatially. So we're looking at all these tokens and looking at, right, how they relate to one another, and that leads to good grouping. But on the other hand, the channel side, the processing is just done through MLP, right? And it's just done locally here. The spatial local, is just local. And so that's the downside, that we feel like this may, right, be not very effective in terms of, and also not a good, issue when it comes to robustness, because, right, you could have large perturbations throw off this MLP here. And so our idea is, can we, in addition, have channel-wise attention? So in addition to attention in space, we also have attention over channels. So in a way, we are looking directly in terms of how different channels relate to one another. For instance, if some channels have overlap or redundancy, right? So we can exploit that better, we can enhance that, and that should lead to better clustering or better grouping. And then the question is, how do we make this lightweight? Because if we did the standard self-attention on channels, that would be quadratic, and that is too expensive. And so we do a more lightweight, an approximate version of attention instead. And that turns out to be a good trade-off. I hope that makes sense.
All right, then let's thank the speaker once again for this excellent keynote.
Thanks so much, and enjoy the rest of the conference there.